Okay, so let me start the presentation. I start from the modular multilevel converter and its control because that's the thing that I use all over my PhD study. So modular multilevel converter is a new type of voltage source converter, but it's not totally new. It's been used for 20 years. But it can be controlled in different kind of moods. As I circle here, it can be grid following moods, which is controlled as a current source, and it can be grid forming moods, which is controlled as voltage source. Working on grid the inner current loop may help to avoid oscillation in medium frequency range. Like people may ask me why. I can tell you the reason that I understand of this. If you look at the grid following MMC, because current control is necessary for grid following MMC, none of them have a very severe negative phase, capacitive phase here. So that just tells me the current integrator was dominate, the integrator in current control dominate this frequency range, which is bandwidth of current control. And if you have an inner current control loop, that inner current control, the integrator of current control can provide you damping to make you have a lower phase here. So that's why you see a lower phase in medium frequency range right around the current control bandwidth. I also put a plot with this MMC, but also including a filter in voltage loop. If you see, that's normal. That's normally how people did in real world. Okay, but adding low pass filter doesn't really solve that. It can solve the high frequency issue, but didn't solve the medium frequency issue totally. And this is like, I mean, this confused by people for a long time. I think some of the engineers trying to optimize this bandwidth of this low pass filter, but they cannot solve it. So before I'm talking about the reshaping methods, I want to quickly go through some of the modes of medium frequency and high frequency oscillation. So this one is a grid following MMC with a grid voltage feed-forward loop. You see that it can have multiple oscillations, and you have medium frequency, high frequency. For the MMC, grid following MMC with heavy filter, but in VDC-Q mode, you have a better passivity, but they still have instability points, and you have a less damping points, which is close to unstable. And if you work in MMC in PQ mode, still the same system, the negative damping becomes severe, and the condition becomes too unstable oscillation. And for the grid forming MMC, you know, grid forming MMC usually for HVDC, it connected to a wind farm, and before the wind turbine connect to the system, you have to use grid forming MMC to charge in the cable first of all, and then connect the wind turbine. So you have two systems. One is before turbine connected, you have MMC connected to cable system. But with different amount of cable, you have a different oscillation frequency, like from 100 hertz to from 1000 hertz to 100 hertz from this trend. And even if you connect the turbine, different amount of turbine connect forms different kind of like oscillation with MMC. So it just tells you that to deal with medium frequency and high frequency reshaping, you have to consider the AC system. You have to consider that the system can change. That's challenging. Existing impedance reshaping methods in the literature was listed here. I mean, for the active reshaping methods, people doing, most of them trying to resolve the, trying to reshape the MMC to be passive in medium high frequency range, but I have to admit, none of them can do it. So I don't think they found a good way, but I think I found a way to do that. So I will explain to you guys later. So the first impedance reshaping control is called wideband reshaping. And what I'm trying to do is same as what other people want to do. Try to eliminate negative damping of MMC, or those negative resistance behavior of MMC in the complete medium of high frequency range that is above 100 hertz. Sounds impossible, right? But let us see how I do it. So let us start from the grid following MMC. So in the left top, the simplified impedance models for MMC in different control modes are shown here. If we look, we know the root cause of the negative damping is introduced by time delay, and you cannot eliminate that. So how to cancel this? What I can think is not cancel delay, it's cancel the control loop. So the process is like this. First, we know the grid voltage feed-forward loop is a big problem. So we use a heavy filter, okay, or cancel it. Then we just cancel that grid voltage feed-forward loop to remove that big trouble. And then we can summarize the three transfer function in a single form, including AS and BS. What is AS? Well, AS are the terms in the blue box. What is BS? BS is a term in the purple box, or it can be 0 in these two transfer functions. Can we cancel the transfer function AS and BS in some way so we can eliminate the delay effect? Yes, we can introduce current or voltage feed-forward terms. Current term will be at numerator, voltage term will be at the denominator. Now we have two directions to cancel AS and BS. The first one is use YIS cancel AS and YVS cancel BS. Is that reasonable? No. If you do that, you just have no controller, or your MMC is equivalently working in open loop control mode. The other way would be better, which is use current feed forward to cancel voltage effect and use voltage feed forward to cancel current effect. And you didn't lose your controller, but you also cancel your delay effects from the impedance shape. So then what you get is REQ and plus SLEQ. It's fully passive. And how to similar things for grid forming MMC, but it's reversed. You have to use a current feed forward to cancel voltage control and use a voltage feed forward to cancel current control. One thing I want to mention is loop stability of inner current control may be affected if current feed forward term canceling voltage control effect. But most of the time people use like single loop voltage control, so it's fine. Finding the passivation terms is another story. So I give two examples. One is for grid following MMC. If you have this expression, and let's neglect REQ because that's inherent passive damping. So we don't want that to enroll in the passivation reshaping process. So we just like neglect that part and let this form, this all form equals to SLEQ. And you do a like 8th grade middle school like equation, right? Solving the unknowns. And then you get this expression for the voltage feed forward. Similarly, you can do that for the grid forming MMC to find a current feed forward term, which is like this. And well, the story is not end because the expression here, I show here, it cannot be implemented directly in practical model. Like two small example, one integrator. Can you have an integrator in the system directly use it? No, because if you have a initial value or DC offset, it will be amplified. And DC offset can be treated, can be introduced by a lot of reasons. We can talk about that later. But if you have an integrator, you have to approximate that by an integrator with a high pass filter. And also for the differentiator, you cannot directly use a derivative term because that would amplify noise. Okay, infinite number of noise. So you have to use like it's a high pass like shape, but it's not high pass filter. You to approximate that. As other things for how to implement the other terms, which you might use coupling term as well. With that in a system, we can look at the reshaping result of the MMC in the medium frequency range and high frequency range. Okay, so what you can say is like the MMC, whatever grid following or grid forming, it becomes fully passive in medium high frequency range compared with its original impedance. Okay, that's our expectation because we want this to be R plus SL. And the better thing is it has a zero condition above 300 Hertz for grid following MMC and above 100 Hertz immediately for grid forming MMC. So the system is in a like less damping condition. Okay, so that's the shortcoming of this. People may worry about this effect to low frequency, so you can activate that only when MMC detects the oscillation. So let's see some cases. Okay, so the first case is MMC connected to a long overhead transmission. The wideband shaping is disabled at the beginning, but enabled at t equals to 0.5 seconds. Of course, it damped the oscillation that you have. But if you look at the impedance plot of the system, originally we have two unstable oscillation, one 52 Hertz and 49 Hertz. And with the impedance reshaping widebandly, whatever you move the resonance frequency to some like new frequency, but because you are fully passive, you have like definitely no resonance condition anymore. Okay, that's for grid following MMC. And if you use grid forming MMC connected by a wind farm, if we before we use the wideband reshaping, we see that two unstable oscillation with 1551 Hertz dominated because much more of its difference above 180 Hertz. But after that, yeah, you solve it. Of course, you solve it because you shape the MMC to be fully passive. So you solve the problem in medium high frequency range. But guess what you can get is the bad thing is at 567 Hertz, it's almost 180 degree. That is because your system, the AC system you're connected to does not have enough damping, and your MMC itself does not have enough damping. So that's a stability margin, a very low stability margin. Okay, so two things can be two issues. One, if there is any background harmonics in the close proximity of 567 Hertz, it will be amplified. And the other bad thing is if the system, the AC system, have much more negative damping, the system can be unstable. So this page is talking about the wideband reshaping effect to the low frequency impedance of MMC. I won't dive into details in this page, as I can talk this single page in like more than 10 minutes. But there are two things that I want to emphasize here. First, the voltage feedforward term introduced a parallel stuff with MMC, and the current feedforward term introduced equivalently a series element with MMC. And the other thing is, because you are doing wideband reshaping, you didn't consider its effect to low frequency during your design, but you have to evaluate after you apply those wideband reshaping. Okay, so, but anyway, if you use wideband reshaping, you have no chance to achieve two goals. One is that you cannot avoid unwanted impact to low frequency, it's shown here. And the second thing is that you cannot add more positive damping as I show in the case study, right? You lack the ability to introduce more positive resistance to MMC. That is narrowband damping can complement. So let's go to the next chapter, which talk about narrowband reshaping. Okay, so I've already covered like too much details of narrowband reshaping in my candidacy exam, so I will highlight few key points like today to not repeating stories. Let us see what is the principle of narrowband reshaping. So the left top are the 5 simplified impedance model of MMC in different control modes. If we look carefully, we can see that these 5 equations can be unified to a simple equation. That is this one, okay, in which the GCS are on the numerator of MMC model, and it's circled by the blue box. And for the GVS, it's a voltage-related effect, which is circled by the purple box. Okay, if you assume we are using voltage feedforward term to do impedance reshaping, you will introduce a term to the denominator, but don't forget to including control, because any term, active control, also are impacted by delay. The HDS is a reshaping control that you introduce. Well, I don't like it to be on the denominator, so let me just like put it to, let me put it to be like numerator. I just found a reciprocal, and I can split that to two things. If you look into that, this term is exactly the reciprocal of ZP, and this term is some other things. If you expand that, this one is YPS, which is admittance of MMC, and this is a virtual admittance parallel with MMC. Okay, based on that, you have more chance if you can split the YRS to different YR, and each of the YR tackle a specific frequency range. Then you can have this kind of like behavior. MMC connected by multiple parallel stuff, and each one synthesized to a different frequency, and tackle adding more positive damping to that frequency. That's what I explained in the candidacy exam. Well, is this simple work? No, of course not, because it's not easy to make YRS look like a bandpass filter. You see here, they have delay, they have other plans, they have the control function affects your shape profile of the YRS. So you have to compensate those phase shift or magnitude change introduced to the HDS. And also you have to consider mutual coupling between different virtual admittance, because like it's not just simple put a bandpass filter to different frequency, that's fine. Each of the virtual admittance introduce negative damping to other frequencies, and in your design you have to compensate that mutual coupling effect. This is a vector figure to show that virtual coupling effect and how you can compensate that. Okay. Finally, by considering all the things, you can calculate the gain for each of the virtual impedance, okay, narrowband damping function. The other way to see that, you can use computer to do that. Okay, this is computer friendly. I show like 2 codes, one in Mathematica, one in MATLAB, just to show that it's easy to implement the process of getting the design of those multi-tuned YRS. Well, I mean, the purpose here is not to show that reshaping control damped oscillation, because people can create a cheating simulation to show that, right? What I want to show is mainly focusing on this impedance. If you look at the impedance, in these cases, I'm trying to use 5 or pentatuned YRS to reshape MMC impedance around 5 intended frequency. Look at the impedance part. It reshaped that only within this frequency and make the MMC to be from negative resistance to be positive resistance. And more interesting things, if you look at the phase difference and the real part of the unshaped which is light blue, and the shaped, which is red, you see that the positive part was not only compensated, the negative real part, it's also added additional amount of positive resistance. And the absolute value are the same as the negative resistance. That's because of my design set up through there. I explained that in my candidacy exam. And also, as I said before, you have different control moves, you have different oscillation frequencies. Yes, if you connect the PQ system, a PQ controlled MMC to the overhead transmission, you have inherently two negative damping, indicated by the phase difference above 180 degrees. And you have a 3 negative real part frequency. And these two are very heavy. So if you use I use a triple tune, then you can, the triple tune YRS do what I want him to do, just add more resistance and make the real part absolute value to be the same before and after using the reshaping control. And that is important because if you're just keeping these to be the same, the absolute value to be the same before and after reshaping, you didn't move your oscillation frequency. So you don't need to worry about that oscillation frequency move because of making you change. Okay, same thing for the offshore wind farm, a wind farm connected by wind turbines, similar stuff. But what I want to specifically point out here is, like here I use the double tuned. Okay, that two bandpass filter are using different cutoff frequency or bandwidth. That is because for the oscillation at 218 hertz here is very close to your low frequency range, where the controller are located in, most of the controller are located in. I don't want that affects that, so I use a very small. It tells you that the bandwidth is also some level of degree that you can use or modify. That would be benefit for adaptive control. And okay, I think people may curious that what is the case if you cannot have heavy filtering in your grid voltage feed-forward loop, right? Previous 3 cases are all using heavy filtering in your grid voltage feed-forward loop, so you don't have that resonant peak in your magnitude response. But you cannot have heavy filtering in your grid voltage feed-forward, but you can have a light filtering. So in the last year, in the past like a few months, I was trying to focus on how to solve that, and I proposed an idea to use like hybrid low-pass filtering and narrowband damping, but you have to introduce low-pass filtering in both grid voltage feed-forward loop and current feedback loop. And also, the purpose of this is to put all the negative damping to the, see here, to the low frequency, to the medium frequency range. And then you use narrowband damping to reshape that. But the problem comes in, which is you put all the negative damping from the high frequency to low frequency range. So actually, so the negative damping of MMC, of the filtered MMC is really large. If you look at the YRS would introduce a resonant peak and resonant deep nearby the oscillation frequency. That could lead to a new intersection. It doesn't show in the previous 3 cases because in the previous cases, the negative damping is not too large. You just use heavy filtering to remove the grid voltage feed-forward loop. So negative damping for the previous 3 cases are not large, but in these cases, because you push all the negative damping from high frequency to medium frequency range, you have to compensate a lot of negative damping. That would cause a new intersection if you didn't select the optimal gain, optimal width of the damping range. So that's difficult to solve, and that can be solved by adaptive control. So as I said before, the narrowband reshaping has to know the oscillation frequency in order to program those reshaping control functions. But how can you know this oscillation frequency beforehand, right? Wideband reshaping has no this issue because wideband just directly remove all the negative damping, whatever the frequency is. It's all frequency range, but for the narrowband damping, you have to rely on stability monitoring stuff to detect those oscillation frequency to solve that, to know the frequency that you are interested in. So details of online detection was presented in candidates exam. I have back slides talk about that, but I just want to point out that online resonance detection should achieve multiple goals. One is identify the oscillation as quickly as possible, and you should also identify whether the spectral peak in your spectrum is resonance or not. And an additional algorithm is necessary to know whether the resonance condition disappear or not, because we know the system configuration can change. So you might see some oscillation at the beginning, and then it automatically disappears because of the system changing. So you have to know that. Otherwise, if you just keeping adding dampers or keeping adding reshaping control, you don't know whether it is redundant or not, then your MMC impedance will be like very ugly eventually. So here is a big picture of how the narrowband impedance reshaping control are coordinated with the narrowband reshaping are proposed in chapter 4. The oscillation, like I want to use the analogy, which is like a whack-a-mole. I call this whack-a-mole. Like the oscillation in the system is a mole, and you have multiple moles, you have multiple oscillations, and the hammer is actually the multi-tuned or single-tuned, the YRS. The narrowband reshaping stuff. So if you play the whack-a-mole, you will see you will have only one hammer, right? But here, I know I have multiple moles, so I don't want them to shoot. So I have to use multiple hammers, okay, multi-tuned hammers. So here you see a 3 oscillation, 3 moles, and you find the first one and you tackle it. Just use a single-tuned hammer, single-tuned YRS, and then the other 2 still exists. Then you use double-tuned. How to design that based on what I said in chapter 4. You just like kill that 2 moles, and then you still have another one left, right? Just use the triple tune and so on. So that's how I try to explain the multi-tune adaptive impedance reshaping. Okay, and the most important thing is also the detection. And as I said, you have to have algorithm to know whether the random condition disappear or not. I think I covered this as well in my DCE. This is a 2 algorithm A and algorithm B. One for adjusting the damping control bandwidth and the gain in a fixed step, and this one is to remove redundant redundant impedance reshaping controllers. I think in the DCE, I propose to use adaptive method to regulate gain and the bandwidth. So here, what it is, okay, the idea is using PI controller, but what is the input? Input is the error between the spectral peak value. The spectral peak has been already identified as oscillation. That's the requirement. And then you compare this with a threshold value. You detect it as also, you treated that, you use that threshold value before to find that oscillation, to identify that oscillation. You compare with them, put the error into the PI controller, and generate a gain there. Okay. Design of the PI controller should consider the dynamics of the. For example, if we use a very large gain, very small error will add a big gain to your system. The system will be like immediately die. Or from now on, okay, I want to show, the most interesting work that I did in my PhD, which is like demonstration of the adaptive narrowband impedance reshaping. I think from my perspective, it's interesting. So let me just, I think it's a video, so I have to, okay. So this is a grid following MMC connected to long overhead transmission as we see before, okay. But if you have adaptive narrowband impedance reshaping, what happens? So at the beginning, we can use a laser here. At the beginning, there's a transient. So transient is not oscillation. So you avoid detecting a wrong oscillation. And then you detect the first oscillation, the spectral peak. Then you program a single tune. And the second oscillation comes, second mode comes. Use a second hammer, which is multi-tuned hammer. You see, gain for each of them has like a KD1, KD2. So it's double-tuned hammer to tackle this 2 mode. And then you disable the first like impedance reshaping control because you want to know whether the mode is still alive or not. Okay. When you disable that, you see that mode comes out again. Then you reactivate that double tune, and you can do this like repeatedly in the future until these 2 oscillations disappear. The other things, which is a grid following MMC to a grid variation. Okay, so the system can vary, and when the system varies its configuration, it is possible that the previous detected oscillation disappear. That is means like the mode change. The mode A goes away, gone, and the mode B comes. So you cannot say, okay, I use a double-tuned hammer to tackle only one hammer, only one mode. So you have to know whether the previous oscillation disappear or not. So here is what it looks like. At the beginning, there's a 100 Hz, 10 Hz also transient. Your algorithm helps you to avoid detecting that transient to be threshold value. See that this trending magnitude is above threshold value you use for detection. And let me run again. So at the beginning that you see the first oscillation because you connected to a grid from grid 1 to grid 2. So you have a first oscillation. At t equals 0.5 seconds, you change your grid to grid 3. And you have a new oscillation at other frequency. But after you detect this oscillation frequency, you first apply double tune damper instead of single tune. And then you disable the early one and to see whether the earliest oscillation appears again. No, it doesn't appear anymore. So you just sustain that also double single tune. You have to update your impedance reshaping to single tune and sustain that impedance reshaping control synthesis at 2603 Hertz. Oh, another thing is more interesting because when you have wind farm, you have two stages. First of all, you have charging cables, and you have oscillation with cables, and then when the wind turbine connected, you have to damp the oscillation between MMC and wind farm. And you know, like before, based on what we know, when you detect the second oscillation, you have to use double tune first of all. But that's not the real cases. Let's first see how the system looks like. So at the beginning, when you're charging the cable, you see an oscillation, you damp it, and turbine start to connect it at 0.6 seconds. Turbine connect, you see an oscillation again, and you damp that, and you are using double tune. But when the wind farm goes into a full power operation mode, right? Full power operation mode, you try to disable the previous damper to see whether the oscillation frequency changed. Yes, it changed. Okay, so here I also plot the impedance, okay, to see at the beginning there's a cable between MMC, which is 476 Hertz oscillation, automatically detected and damped. Then you have this reshaped MMC connected by wind farm. It has a new oscillation at 587 Hertz. But this is not the real oscillation because your cable is not existing like lonely. It's connected by wind farms. So the AC system impedance change. So you disable both of the like double tune damper, and you see a new oscillation disappear at 583 Hertz. So you finally tune yourself to this frequency. Oh, that's the real oscillation between a full power wind farm and MMC. And this part is a new walk. So as I said, if you use low pass filtering in your grid voltage before loop, but not heavy, and you also use a current feedback in low pass filtering, you push all the negative damping from high frequency to low frequency. Design is in my backup slides. But how to determine the narrowband damping here? You cannot use any of the fixed design methods or give a fixed gain. No, you have to find the optimal point, which is give you minimum gain and minimum bandwidth. So let's first see how the system automatically works. So when you detect the oscillation, you sustain at some level, and then you further tune the sustain some level until your system becomes stable. And people like, I really would like to go back to certain points here. Sorry, I think I can do things here. If we go to the immediate beginning of the oscillation, we see that the oscillation was damped because your MMC automatically, your damping control automatically tuned yourself to tune the damping control or reshaping control to some level and try to sustain there, but they immediately see a small oscillation. So they further change the gain, okay, and finally sustain at this level. So if you look at the things here, all the oscillation was damped. But did you see a small like right-on harmonics here? That's something because of this is still not the optimal point. If you keeping asking this, like you see that small right-on harmonics keeping increasing until some level, it was identified. Compared with here to before, the right-on harmonics is increasing slowly. But finally, it was identified as a small growing oscillation. Then you further tune your damper. What is the result of the further tuning? That gives you a completely stable system. I want to expand that by impedance. Okay. So in the first stage, when you sustain that, you actually put your system to be this frequency, to be like this, which is this black dash line. It has that 182-degree phase difference. Although it removes the previous readiness condition, but introduces a new condition, which is slow growing. Until it was identified, it was further tuned your system impedance, reshape it to be like the red line, which is having a 179-degree phase difference. Then the system becomes stable. It's an optimal point. Okay, so from here to the end, I think it's some of the research output from my intern. So my intern work is focusing on like HVDC, MMC-based HVDC protection control. So it's more about deal with large system transient, large current, fault current. So I learned something from my previous work, which is using active control, you can reshape your impedance. So in your fault condition, you also have a circuit, including MMC. And the MMC can be represented by this like simple LC, ILC stuff. I just try to know if I can reshape this impedance, then I can try to manipulate or modify the DC fault current level. So if you do a state-space average model to represent the DC fault current, you see a small d, which is duty ratio, and the LEQ, which is the equivalent arm impedance and the DC reactor. If you can do some change to these two values, you can just finally reshape the fault circuit, the MMC fault impedance. The first thing I propose is a virtual arm impedance-based reshaping. So I introduce additional feed-forward loop of circulating current because DC current is not goes to AC side, so it's circulating current. And when you reshape the impedance, if you look at the beginning, it's only LC, and if you reshape the impedance, you add multiple RL sections because of this controller. So you make your MMC looks more inductive. Like inductive stuff can resist the current increasing. And how to design this, you have to consider loop stability, and you have to consider small signal stability of the MMC DC side impedance, because you don't want to introduce negative damping too much and cause oscillation issue. Another thing is how to modify the duty ratio. I was using something I proposed in my DCE, but I haven't covered that part. I just use part of the energy control that I proposed before. I use a zero sequence circulating current in between to regulate that duty ratio by regulating this VZ generated by this controller. And the duty ratio can be approximated, affected by the design of the zero sequence circulating current control. And because of the energy is related to, when you have a MMC submodules, you have discharging of submodule capacitor, you have energy change, then you will automatically activate this like duty ratio modification stuff. Design should consider the small signal stability based tuning. Okay, so let's see the performance of the fault current limiting after the impedance reshaping. If we manually blocking some modules at t equal to 1.0005 seconds, we just like to see what that happens. Okay, after that, so it's not necessary. We can see that in different cases we apply no fault current limiting control, no fault impedance reshaping, and we have different fault impedance reshaping. We see that by using our proposed impedance reshaping, we have less amount of DC side current and less amount of arm current. Okay, what that means? That means your inductive stuff you reshaped or you purposely added rarely behaves when the fault occurs. The conclusion and future work, like simplified impedance model of MMC was derived and wideband reshaping methods was proposed. The adaptive narrowband shaping has to be used with the multi-tube narrowband reshaping to make it effective. Online algorithm to identify oscillation and identify the disappearance or new appearance of other oscillations should be have. I have already presented that. Impedance reshaping control can also be extended to modify the large impedance model, which is state-space average DC impedance. Then you can resolve some system transient behavior by reshaping MMC impedance. So future work, including like different sequence separation technology, I think that's something Professor Belmont mentions in my DCE. So I saw people using delay signal cancellation already in the literature and model the impedance. So I think what I can do in the future can compare other sequence separation method, which is like DDR, SRF, and desogging. So, and compare with their effect to MMC impedance shaping. And also extend the multi-tune impedance reshaping to DC side. I'm dealing with all the things AC side, but DC side can still have long transmission, long cables. So you still have issue in DC side. I have to extend that to DC side to see how I can use what I propose and to solve problem there. And also you can use multi-tune impedance reshaping to mitigate amplification of multiple background harmonics. Okay, that's another topic. Implement the adaptive impedance reshaping to a demo project. I mean, I have friends working in China, April, but they read my paper and they are interested to it, and they have like interest to implement that in a demo project in China. So I hope that I can finish that, or I can have the cooperation with them. Finding other ways to detect oscillation by using advanced signal processing methods. So if you recap what I use, I'm using interpolated fast Fourier transform. That might not be the best one, but I think that's a good one for right now. Publications. So I have like 2 journal publications in IEEE transactions with Luigi, and I also have like multiple, 7 conference paper. ECC and Compare are all like top conference, and ISGT as well. I mean, whatever I do here in the conference paper, I think I can generate them, like add more stuff there to make it expand them to be a transaction paper. But I was very like lucky to have 2 transaction paper in last 1.5 years. And I would thank you, my committee members, Dr. Van Frenti, Professor Gonjulius, and Professor Carr, Professor Gomez Belmont. I think in the PDF I sent you, I might like mistakenly spell your name like Mr. U or Miss L here, but I rectify myself, okay, by your discussion. So all current and past members of Luigi's lab, OSET lab, and I want to thank you some people. Shahir Shah from National Renewable Energy Lab, he's my mentor during my intern. And Han Chao, a previous student of RPI, he helps a lot on my study and my life suggestions. And my previous advisor, Payman Hanyang, and my undergrad professor, both of them give me a lot of suggestions when I having troubles with others. And I also want to thank you family members and friends, and also ECSD department. Without like help from Professor Wen and Professor Abazadeh, that I cannot like pass through a lot of like troubles. Okay, so that's all my presentation for today. I think backup slides may include more things that you are interested to.
Okay, thank you very much, Pengxiang.